Welcome to this explainer. Today, we're focusing on something that is absolutely foundational to polymer science and product design, and that is demystifying impact testing methodologies for plastics. I am thrilled to guide you through this because, honestly, understanding how and why a material breaks under sudden stress, well, that's exactly what separates a brilliant, reliable piece of engineering from a complete and catastrophic failure. We're going to take our time today and look really closely at the exact tools, tests, and standard methodologies that engineers and material scientists rely on worldwide. Okay, let's dive right into this by asking a very practical, real-world question. What actually physically happens when a plastic part fails under a sudden load? Think about it. We're talking about a plastic car bumper in a low-speed collision, or maybe a polycarbonate bicycle helmet suddenly striking the pavement. We aren't talking about slowly and gently stretching a material until it eventually snaps. No, we are talking about high-speed dynamic shock. The real-world stakes of these sudden impacts are incredibly high. They literally dictate whether a product is going to protect a life or just shatter into a million useless pieces.
So, here is our roadmap for today. We'll start with why impact testing matters, look at the testing toolkit, and then dive deep into the IZOD and CHARPY tests. After that, we'll do a head-to-head comparison of those two and wrap up with testing films using the falling dart method.
Let's start with Section 1, Why Impact Testing Matters.
Now, what's really fascinating about impact failure is how it highlights the contrast between two fundamental material properties, toughness and brittleness. Toughness is essentially the total energy a material can absorb before rupturing. Now, in a standard slow-speed tensile test, this is just the area under your entire stress-strain curve. Simple, right? But under high-speed impact, toughness behaves completely differently. It is entirely dictated by molecular flexibility. Think of polymer molecules like a tangled bowl of spaghetti. If those polymer molecules can quickly disentangle and respond to a sudden, violent mechanical stress, like they do in flexible vinyls or polyethylenes, the material behaves toughly. It absorbs the blow. But in stiff, rigid polymers like polystyrene, those molecular segments are essentially trapped. They can't respond fast enough to that rapid stress, which leads us to our second definition, brittleness. Brittleness is the inability to experience any significant amount of strain without rupture. It just snaps. And here's the kicker. This is highly temperature dependent. If you cool an amorphous or semi-crystalline polymer down below its glass transition temperature, it suddenly becomes extremely brittle. It's like freezing that bowl of spaghetti. Hit it and it shatters.
Moving on to Section 2, the Impact Testing Toolkit.
So, how do we actually measure this? Well, the standard tests used in labs essentially fall into two main categories: pendulum tests and drop weight tests. The pendulum family is exactly what it sounds like, a swinging hammer. This includes the IZOD, CHARPY, tensile impact, and chip impact tests. These usually strike a specific rigidly held machine specimen. On the other hand, drop weight tests, like the falling dart or free-falling weight methods, are incredibly useful for a totally different reason. They introduce polyaxial or multi-directional stresses. This much more closely simulates real-world conditions for things like flat, rigid plastics, thin packaging films, and extruded sheets. For this explainer, we're going to focus really deeply on the big three: IZOD, CHARPY, and falling dart.
All right, Section 3. Let's get into the details of the IZOD impact test, which is defined by the widely used ASTM D256 standard.
The IZOD apparatus you see here is an absolute industry workhorse. It's used extensively across the field of polymer science for quality control and for establishing critical material specifications. Now, let's look at its parts. It consists of a very heavy base, and it has to be heavy to prevent any energy from being lost to vibration, a sturdy vise for clamping the specimen securely, and a pendulum hammer swinging from a fixed, almost frictionless axis of rotation. The pendulum is equipped with a specially hardened steel striking nose, so you lift the hammer to a set height, locking in its potential energy. When released, the pendulum swings down, breaks the specimen, and swings through to the other side. As it does, a friction pointer on a dial mechanism gets pushed along, and this indicates the excess kinetic energy remaining in the pendulum after the break. The energy the pendulum lost is exactly the energy it took to break the plastic. It is an incredibly elegant, purely mechanical way to measure a material's impact absorption.
But listen, the testing machine is really only half of the equation. The specimen itself has to be rigidly, perfectly standardized. And this brilliantly illustrates just how meticulous material testing really must be. The standard ISO test specimen has very strict dimensions, which you definitely want to remember. It is 63.5 millimeters long, 12.7 millimeters wide, and typically 3.2 millimeters thick. Now, notice that little notch precisely cut into the side. That notch is crucial. It has a 45-degree angle, a 0.25 millimeter radius right at the tip, and a total depth of exactly 2.54 millimeters. Now you might be wondering, why go to all this trouble to carefully cut a notch into a perfectly good piece of plastic? Because that notch deliberately provides a high stress concentration area. By intentionally creating this weak point, we force the sample into a brittle failure rather than a ductile, stretchy one. This prevents plastic deformation from totally skewing our measurement, allowing us to find the material's true basic notch sensitivity.
So how do we actually run this test on the lab bench? The procedure goes chronologically like this. First, we take our conditioned specimen and clamp it vertically into the vise. It acts just like a cantilever beam. Think of a diving board sticking out over a pool. Crucially, you must ensure the notched end is facing directly toward the striking edge of the pendulum. Second, we release the pendulum hammer from its fixed Loctite. It swings down, violently strikes the specimen right above the vise, and follows through. Third, we read the impact values directly from that analog scale, which tells us the raw energy absorbed in joules. Finally, we calculate the actual impact strength. We do this by taking the total energy absorbed and dividing it by the cross-sectional thickness of the specimen exactly at the notch. This math gives us a standardized value, usually in joules per meter or kilojoules per square meter. And that standardized number is what allows us to compare entirely different materials fairly.
However, as an engineer, it's vital to know that IZOD results aren't just magically absolute numbers. They are highly sensitive to several testing variables. Specimen thickness and how flawlessly smoothly that notch is cut play a huge role. A jagged notch ruins the test. Temperature is massive too. As we talked about earlier, lowering the test temperature drastically reduces impact resistance as the material approaches its glass transition and becomes brittle. Polymer orientation also matters heavily. Because of how polymer chains align during injection molding, impact strength is always higher if you test in the direction of the polymer flow. And, of course, the inclusion of fillers, glass reinforcements, or specific chemical additives will fundamentally alter how the base material absorbs shock.
Let's transition to Section 4, the CHARPY impact test, governed by the ASTM D6110 standard.
Now, the CHARPY test is a close cousin to the IZOD. It uses a very similar pendulum testing machine. In fact, many modern machines in university labs have a reversible vise designed to accommodate both tests. But take a close look at the specimen's setup. Notice that the V-notch is placed exactly in the center of the bar. The CHARPY test fundamentally changes how the specimen is positioned and where exactly it is struck by the hammer. Because of these differences, it is often the preferred choice for testing certain specific types of thermoplastics, like polypropylene.
The crucial point here is the procedure. Pay close attention to how this differs from IZOD. In the CHARPY test, step 1 is to place the specimen horizontally. It is supported at both ends, but it is entirely unclamped. It just rests there, acting as what engineers call a simply supported beam. Step 2 is absolutely critical. You must ensure the notch is facing strictly away from the striking edge. When the pendulum is released in step 3, it swoops down and hits the exact middle of the specimen, on the flat side, perfectly opposite the notch. Finally, just like the IZOD test, we read the dial for absorbed energy and calculate the impact strength.
Section 5, the IZOD versus CHARPY comparison.
This visual side-by-side perfectly illustrates that core distinction we've been talking about, and it's a great way to lock this into your memory. On the left, we have the ISO test. Notice how the bottom half of the specimen is rigidly clamped vertically in that vise. It stands up straight as a cantilever beam, and the striker hits the top half, on the exact same side as the notch. Now look over at the CHARPY test on the right. The specimen lies completely horizontal. It just rests on those two supports at the far ends, a simply supported beam. The striker hits right dead in the middle, and importantly, the notch is pointing downward, facing completely away from the impact point.
Let's really solidify those exact mechanical differences with a quick summary. Position: IZOD is vertical, CHARPY is horizontal. Notch direction: the IZOD notch faces directly toward the pendulum striker, while the CHARPY notch faces completely away from it. Striking point: IZOD strikes the upper, unsupported tip of the specimen using what's called a farming hammer shape, while CHARPY strikes the exact center of the beam using a ball pin style hammer. Understanding these geometric and mechanical changes is absolutely vital. Why? Because they entirely alter the stress distribution inside the plastic during that split-second impact, which is why a material might test differently on IZOD compared to CHARPY.
Moving on to Section 6, testing films with the falling dart method.
Okay, so what happens when pendulum tests just don't work?
If you try to swing a heavy pendulum at a thin piece of agricultural film or a garbage bag, it's not going to give you useful data. We have to pivot. The reality is that pendulum tests generally measure the notch sensitivity of a thick, rigid material in a single, perfectly controlled plane. They simply do not duplicate the multidirectional or polyaxial impact stresses that thin films, packaging sheets, or even finished blow-molded dawdles experience out in the real world. To measure the true practical material toughness of these products, we use drop weight tests, and specifically the free-falling dart method.
For testing plastic films, we use standard ASTM D1709. The procedure here is straightforward, but it is highly effective. First, a sample of the film is secured flat and pulled taut in a circular clamp over a hollow base plate. It looks kind of like a drumhead. Second, a round-headed hemispherical dart is dropped straight down through a vertical guide tube right onto the center of the film. The ASTM standard actually outlines two methods. Method A drops a dart from a fixed height but varies the actual weight of the dart by adding little metal discs to it. Method B, conversely, might vary the drop height for a fixed weight. The ultimate goal in Step 3 is to systematically dial it in and determine the exact kinetic energy or the exact weight required to rupture the film 50% of the time. It is a fantastic practical simulation of what happens when something is suddenly dropped onto a taut plastic sheet in real life.
Now, what is truly fascinating about modern materials testing is the incredible leap into instrumented tests. Standard drop tests, like the basic falling dart, just tell you a simple pass-fail. Did the film break and at what energy? But if you instrument the falling dart's tip, or even the IZOD pendulum's hammer, with tiny, highly sensitive piezoelectric load cells, it completely changes the game. Connected to high-speed data acquisition systems, these sensors generate continuous microsecond by microsecond curves of force, energy, and deformation versus time during the exact violent millisecond of impact. This is huge. It allows polymer engineers to see exactly how much energy went into simply initiating a microscopic crack versus how much energy was spent propagating that crack until the part failed. It gives us an incredibly nuanced, deep picture of a material's true toughness, and it precisely pinpoints things like the ductile to brittle transition temperature.
Before we wrap up today's explainer, I really want to highlight exactly why engineers must constantly test things, and never, ever just assume. You might logically think that taking a plastic and adding strong, rigid glass fibers to it always makes it tougher. Actually, no, that's not true at all. Adding 30% glass fibers to polycarbonate, which is already a super tough plastic, drastically reduces its IZOD impact strength. It plummets from a highly tough 15 foot-pounds per inch down to a brittle 3.7. It ruins the toughness. However, take a naturally brittle plastic like polystyrene, add that exact same 30% glass fiber, and its impact strength more than doubles. The complex chemical and physical interaction between the base polymer matrix and the filler fundamentally flips the impact behavior. You just can't guess. You have to test it.
Which leads us to a final provocative thought. We've seen today how a microscopically precise notch, a slight drop in room temperature, or even the tiny molecular direction of polymer flow can literally be the difference between a part surviving a crash or shattering into dust. If traditional manufacturing is this unbelievably sensitive, how must we adapt to these rigid, decades-old testing standards, like IZOD and CHARPY, for the incredibly complex, multi-axial internal structures of modern 3D printed polymers? Understanding the IZOD, CHARPY, and DART tests isn't just about passing a university exam or memorizing formulas. It is the absolute critical baseline for designing the safe, failure-proof materials of tomorrow. Thank you so much for joining me on this explainer. Keep questioning, keep testing your materials, and I'll see you in the next one.